symbol that we used when we type stuff up. However, the true symbol for a vector is, like I said, just the line and like the top part of the arrow. So not both parts of the arrow. If we were looking at it this way, we think about these as like rays in geometry, although there's going to be some similarities here. But these do have an initial starting spot and ending spot. When you hear the word scalar multiplication, it means we are scaling something up or scaling it down. And it means you're being multiplied by something. So if I want to scale the size of something up by 2, I'm multiplying it by 2. Okay, if I want to scale something down by a half, I'm multiplying by 1/2. So whenever you are multiplying or changing something in terms of the magnitude with multiplication, that's a scalar. Things that are examples of magnitude are length, mass, area, and temperature. To describe the displacement of an object, 2 numbers are required. So again, we need the magnitude and we need the direction, which we learned back in Minions a lot of years ago and we didn't even realize it. To describe velocity, we talk about speed, so how fast something is moving and the direction. There are several quantities that involve magnitude and direction. Displacement, velocity, acceleration, force is a type of problem that we'll learn how to do as well. So yes, some of the story problems are kind of tricky, and that might be what you heard about from this chapter. So we have a vector in the plane. So you're going to have an initial point, and you're going to have a terminal point where it ends, and you're going to have a direction of how you got there. Okay? The length of the segment is called the magnitude. So the length is called, oh whoops, let me put that up a little higher so you can see it better. The length is called the magnitude, and it's denoted by, so we're going to pretend we have this same vector AB. So when you see AB written as a vector, but inside of what looks like some absolute values, that means magnitude. Okay? And we're going to get a formula for the magnitude as well. Not today, but down the road we're going to get a formula for magnitude. There's lots of notation stuff in this first section, so lots of like little things to get comfortable with and remember. All right, 2 vectors are equal if they have the same direction. So they have to be traveling in the same direction, and they have to have equal magnitude. So same direction and equal magnitude mean that we have the same vector, or that 2 vectors are going to be equal to each other. We can represent vectors in different ways. So you're going to see a lot of different kind of formats. Sometimes we address them by the initial and terminal point and then have that symbol on top. Sometimes it just gets a single letter name. So think about a line for a minute. So think back to geometry. If you had line AB, right? You could write AB and you could write it with a line over top, but you know how sometimes we say, oh, it's line L, like we give it a name. So that's the same thing here. So we can talk about it based on its initial and terminal point, or we can just give it a name. Okay? We have to think about both the horizontal component and the vertical component. So if you think back to last chapter, or even just the quiz that you took yesterday, oops, I lost an M. Or even just the quiz you took yesterday, we had A's and B's, right? And the A was our real number, and the B was the coefficient in front of our imaginary part, yeah? We're going to have A and B again. The notation is going to be just a little different. Look down below. It looks like this instead of what we've had. So not parentheses, but we've got like this symbol. So we are going to have A and B again. A is going to represent the horizontal component, and B is going to represent the vertical component of our vector. Okay, so we come down here, and here are some examples of what a vector v could look like. Now, if we don't know where the vector originates, if we don't know the initial point, there are lots of different ways that we could draw a vector v if we know what a and b are. So do you see for all of these that a and b are the same, like this A, this A, this A, and this A are all matches? Okay, and the same with the b's. So the vector can have the same direction and the same components, A and B, but if we don't know precisely where it starts, any of those could be representations of our vector. So far, so good. We're okay? Okay. Let's flip. Oh wait, do I want to say something else? Oh, let's do this question. Yeah, I do. Just kidding, I do want to say something else. What is the difference between this format? So this format, if we're given something like this, is giving us the magnitude and the direction. Gives us the magnitude and the direction. And we're going to get an equation for that. Not today, but tomorrow. So that's what these are based off of. So to find A, you'll have those two components multiplied together, the magnitude and the direction. And then if you have something like this, this is just a point. This is just a point off in space. So you're very much so looking at, is it parentheses? Do I have kind of those triangle things on each side? Like, what does my notation look like? Because that's going to help you understand, like, what's going on and what you're being given. When you're ready, you can flip. Now I'm ready to flip. For real this time. Okay. So you can start adding what I've got here. To find a vector v, and we want to find it represented in the plane with the initial and terminal point. The vector v is going to be written, you're going to take your x2 minus x1, comma y2 minus y1. So you're taking your terminal x value minus your initial x value, and that'll go here. You're taking your terminal y value minus your initial y value, and that'll go here. So we're going to do some examples to look at this. So, like I said, day one of this information, not super tricky. So I'm over 2, I'm up at 1, so 2, comma, 1. And then I'm over at -3, I'm up at 1, 2, 3, 4. Okay. So those are just my ordered pairs. See how I put parentheses, right? Like I'm just saying, hey, this point is this, and this point is this. Okay? And it even tells me, oh, I could have just looked over here. Oh, no, but that's not right. Oh, it must be a different problem. I was going to say. We had similar numbers, so I was looking at it thinking it was the same. That's a separate one. Okay. We want to put it in what we call component form. So we're going to take our terminal minus our initial for each one. And I'm going to write it out in 2 steps. You might not need 2 steps, but I want you to be able to see where the numbers came from the first time. Okay, so we're going to start with terminal minus initial for x. So if I go to my x coordinate, terminal is q, initial is p. So if I do terminal minus initial, I'm going to have -3 minus 2. And that's going to go in that first spot. So this is component form. And again, just looking at that horizontal component. Now let's look at the vertical. Again, terminal minus initial, 4 minus 1. So my component form is going to be -5, comma 3. Again, do I really think you need 2 steps to do the subtraction? No. I just want to make sure that if you look at this down the road, you're not like, well, where did those numbers come from? Do you know what I mean? Okay. Next one is asking us the same thing, but we don't get a picture. So we're going to do, again, terminal minus initial. Let's see. Initial point P, so I'm going to assume this is initial as well, and this is my terminal here. So terminal minus initial, 5 minus 2, 3. Terminal minus initial, 4 minus -1, 5. So again, you're looking at each component separately from each other, looking at the x's and then looking at the y's, and we're subtracting, so we're being careful with any negative signs that we might encounter. Could we be asked to graph a vector? We sure could. They tell us our initial point is at 4, 3, and then I'm giving you this information, so if you haven't already added that, please do. It looks like in the past maybe this is where we've stopped for day 1, but we're not going to stop there. We're going to keep going. Not a lot further, but a little further. Okay, so 4, 3 is my initial point for both of these, part A and B. And then notice that it gives me my component form. So we're going to have to work backwards and figure out where the terminal point lives. All right, so my initial point is at over 4. 1, 2, 3, 4, up, 1, 2, 3. So it's the same thing for both. Here's my initial point for both of them. Lovely. Now we need to work backwards and figure out what our terminal point is going to be. So, my terminal value for x, remember it's terminal minus initial equals the value from the component form. So let me say that again. I'm using the same formula that we used up here. We don't know where the terminal point is. That's what we're trying to find so we can graph it. The terminal point, whatever it may be, minus the initial, and again, we're looking at just the x component right now, is equal to 4. And so then we'll figure out in a second what must t of x have been, because you can solve that in your head. These aren't really bad ones to solve in your head. T sub y is going to be terminal minus initial equals the y value here. All right, so what must t have been in terms of x? 8. And then the terminal point in terms of y must have been what? 0. Okay. So I'm going to graph the point 8, 0. And I'm going to be probably a little bit off the grid, but that's okay. So 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to say it's about here. And if you want to draw it in and put some more tick marks in there, so let's see, 5, 6, 7, 8. And then we need to draw in our vector. So we're going to draw it in from the initial to the terminal. And we're also going to put an arrow on there to show that this is the direction we went. So this was my initial spot to the terminal spot. So not normally something we do showing which direction we went in, because when you think about a line or a parabola or whatever you're graphing, you graph it. You're not thinking about order, like what do I start with? Bless you. In this case, we're thinking about what do we start with. All right, let's play the same game over here. All right, so the terminal minus the initial equals the component form value. For y, the terminal minus the initial equals the component form value for y. So again, we're going to find the terminal point. So what would have had to have been here for t sub x? What would my terminal point be? -4 and 2. So I'm going to go -4, 1, 2, 3, 4, and up 2. Here's the point. And again, normally we just connect them, but today not only do we connect, but we say, hey, this is where we came from, this is where we headed to. Again, we're going to go just a little bit further and have some homework tonight. So we're going to talk about adding vectors next. So we can do things with vectors. We can have multiple vectors and we can combine them. We can add them. We can subtract them. We can multiply them by scalars. There's so many things that we can do with our vectors. So, if the displacement of u equals, and there should have been a blank here, but there wasn't. So let's say the displacement equals vector AB. And then let's say vector V is the displacement BC. If we were to add those two vectors together, it would give us this vector AC. So you would add each component up, and it would take you from one to the other, from start to finish. So that would be what it would look like in terms of the picture. So it would give us vector AC when we add them together. In other words, the single displacement represented by the vector AC. So again, AC is the single vector. It's the sum of AB and BC. Has the same effect as two displacements together. So you can think of it backwards as kind of breaking it apart into two different vectors. So we call vector AC the sum of vectors AB and BC. And we can even write it AC equals AB plus BC. Again, there's a lot of like little notation stuff in here, and you're going to have some moments where you're like, well, duh, that's obviously true. Like we said that a couple times. So you're going to have some moments like that. Again, this is just as we start going through and getting all this beginning information. All right, next, the zero vector is when you have no displacement. So nothing happened. We got on the plane, and it sat there. And we did not go anywhere. Zero displacement, nothing happened. So thus to find the sum of any two vectors u and v, we would sketch u and v, and then we could find the sum of them. It would go from the initial point of the first to the terminal point of the last. All right, when you're ready, you can flip again. Okay, so we're going to come down to this part, and this is where we're going to stop for today. So if you're like, how far are we going? This far. All right. So those pictures go with what we were just talking about if we were adding u and v together. So here's vector u, here's vector v. It starts from the initial point of u to the terminal point of v. So that's how you're finding the sum of the two of them. Multiplication of vectors. So only thing we're going to talk about today is just what we call scalar multiplication. And so that's where you're taking a vector and you're multiplying it by a number. So maybe you're doubling it, maybe you're tripling it. So the vector AV has magnitude A times V, and it has the same direction that it was going in initially, as long as A is bigger than 0. So think back to chapter 8 for a second. Remember when we were graphing and it was a positive number, we would graph in that direction? Do you remember that? And then if it was negative, we would graph the other way. The same thing here. So if you take a look down here at your examples, these are kind of tiny. And as Ms. Vessel gets older, it's harder for her to read these. So if this is the direction of V when it's positive, that's the direction of V when it's negative. So they're going against each other, okay? So kind of thinking of it as 180 degrees. If I'm traveling this way and then you're thinking the opposite or negative, you're going the opposite direction. So if A equals 0, then AV is the 0 vector, because if you multiply your vector by 0, it's going to be 0. So this process is called multiplication of a vector by a scalar. So we're not multiplying two vectors together. We're taking a vector and we're saying let's double the whole thing. So we're doubling each part, and again we call that multiplication by a scalar. It has the impact of either stretching or compressing. It could do either. So a stretch would happen if your number is bigger than 1. So if you're multiplying by 1.5 or 2 or 10, that's getting bigger and bigger, right? If you're multiplying by a decimal, you're getting smaller and smaller and smaller. So this doesn't have anything to do with negatives right now. So stretch is multiplying by a number bigger than 1. Compression is multiplying by a number between 1 and 0. So the negative numbers have the impact of making me go the opposite direction. All right. So thus we write the vector. So if we have negative v, it's going to be heading in the opposite direction. Like I said, I swear your book is an old soul because it likes to use the word thus. The difference of two vectors, u and v, is defined by u minus v, which you can take the vector u plus the opposite of vector v. So subtraction is the same as adding the opposite. So again, like I said, you're going to have some moments here where you're like, yes, duh, that's true. You've also seen properties like the reflexive property, right? A equals A. That's obviously true. We're going to get back into some of those properties as well and talk about what holds true. Because down the road, we're going to do stuff with matrices. And a lot of these properties that we've known in the past that hold true, like the commutative property, don't hold true anymore. They do here, but down the road we'll see that they don't always hold true. So again, if this is your original vector, here's 1/2 v. Do you see how it's the same direction, but half the length, or magnitude? Okay, keep listening for another minute. If this is my original vector v, do you see how this one is same direction, but double? Okay. This one's headed opposite direction. This one's opposite, and it's cut down by 1/3, right? So we can see the different things that we're doing there. So that's all you're going to experience today. We've got formulas on deck for tomorrow. And then for Friday, for Pi Day, we're going to celebrate Pi Day with some airplane problems. Yay! Okay.